All right, it's my introduction 1 o'clock, so we go ahead and start this month's webinar. Good afternoon. I'm Hoda Azari with the Federal Highway Administration. I manage the NDE research program, and thank you for joining us for another FHWA NDE webinar. And thank you for supporting this webinar series. The objective of this webinar has been to create a platform to hear from different state DOTs and governments and local agencies about their current practices, current application and case studies, challenges, added values, policies, and future application of NDE. So all past webinars has been recorded, and the link is provided in the flyer that I distribute every month. Since 3 months ago, we switched to Teams, from Adobe to Teams, Microsoft Teams, because many of you had difficulty with registering and accessing the Adobe. So we switched to Teams, but due to restrictions in sharing files through the FHWA Teams site, we will be posting the recordings through the FHWA YouTube channel, which will take some time to get approval. So meanwhile, if any of you is interested to receive a copy of the webinars from April, please contact me directly and I'll be happy to share the file, the recording with you from April, May, June, and July this month. PEs who attend the entire webinar as an individual will be awarded 1 PDH, and to be eligible for the credits, you have to stay on for the entire session, including the Q&A session following the presentation. So there is a survey after the presentation, and you will be asked to submit your contact information, your email address, and there is also 2 questions at the survey, and I appreciate your feedback and suggestion to improve the webinar series. And if you have any suggestions for future topics or guest speakers, please share it with us through the survey. This month's webinar is about measurement of modulus in pavement using seismic methods. And we have 2 guest speakers today that will talk about the use of property pavement analyzer or PSPA at the FAA's full-scale accelerated pavement testing facility. And we are very fortunate and pleased to have these 2 guest speakers today with us. Our first guest speaker is Dr. Sohail Nazarian, a professor and director of Center for Transportation Infrastructure Systems at the University of Texas at El Paso. And our second guest speaker is Dr. Garg, the program manager at the National Airport Pavement and Material Research Center of the Federal Aviation Administration. You can type down your question in the chat box and we will address your question after the presentation. So with that, I'll pass it to Sohail for his presentation. Sohail?
Thank you so much. They say that whenever you leave the door open, even virtually, faculty would come in and start lecturing you. So that's me. Can you see my screen?
Not yet. We can, yeah, it's coming.
Okay, I would be brief because NAV has really good case studies that it will be probably of interest to the practitioners more. I'm just going to talk a little bit about the high frequency seismic methods. Is it there now? The slides? And
Yes.
I can see it.
okay, good. So I just called it beyond anomaly detection. A lot of times, you know, with the geophysical methods, we are after anomalies. This is a little bit different. We're going to go after material properties. I would focus on the PSPA, the portable seismic property analyzer, because I'm very familiar with that. But the talk is general. You know, you can use any system that you can run high frequency seismic method. So why focus on seismic? Because you have four attributes. One is non-destructive. The second one is gives you a fundamental material properties, basically the linear elastic modulus of the material. It's layer specific when you have an exposed layer, and more importantly, you can relate lab and field, at least theoretically. If you prepare the specimen and they're identical, you should get identical numbers between field and lab, and you don't need a transfer function. So these are the unique capabilities. When you combine all four of these, that it would be desirable. What's the good and bad and ugly? The good is that you measure a layer-specific fundamental properties, independent if you are running lab tests or field tests on the same specimen. The bad side of it is that it doesn't give you the design modulus that we use in the pavement design, but you can correlate the results from the traditional tests with the seismic modulus to overcome that. And the ugly side is that the learning curve is a little bit steep, simply because we are never exposed to the geophysics or seismic or wave propagation during our undergraduate and most graduate students. So, you know, you have to spend some time to learn. It is not just open the box and start testing. Some of the application is the structural diagnostic. You know, you have seen a lot of it, especially on the bridges in this series. And what I would focus on is the exposed pavement layer properties. And the most relevant tests are impact echo, which I would not talk about it because, again, it has been talked about many, many times. And I would focus on ultrasonic surface waves. So essentially, why are we interested in the surface waves or in waves in general? Because if you look at your physics, the modulus of a material is proportional to the mass density and the velocity of propagation of waves. And we know exactly what modulus we are measuring. This is not the case with other laboratory or field tests. We know we are measuring the initial tangent modulus of the material. What's the concept very quickly is we are working with the surface wave. So the goal is to generate something which is called a dispersion curve, how the phase velocity changes with the wavelength, if you want to simplify it. And if I have a two-layer pavement, as you see over here, just to simplify it, as long as the property of the top layer is the same, the dispersion curve would be a constant value. And as soon as I start going to another material, I'm going to have a transition zone till I get to the second material. And eventually, at the very long wavelengths, the curve becomes asymptotic to the properties of the lower layer. So we want to just, if you have an exposed layer, we want to just focus on that layer. So what do we need to run the test? You need a source and two receivers. Again, I'm showing you a PSPA, but it can be easily two sensors and a hammer. And basically you have to generate high enough frequency. That's the challenge. And basically observe the arrival of the waves at receiver A and receiver B, as you see over there. The black one, receiver A, green one, the receiver B. And the dominant energy is surface waves, so we can work with that. We go through the spectral analysis and we just look at something called a phase spectra that we use to generate the dispersion curve that we discussed. If the material is constant, uniform, the dispersion curve would be constant. If not, it would be varying depending. If it's getting softer, it's going to go this way. If it's going to go harder, it's going to go the other way. So you get an indication of the uniformity of the material. For simplicity, we're just going to go on average over a certain range that you're interested in for the practicality. If you are interested in delineating layers, then you can go through an inversion process and do that. Some of the uses, I'm just going to go very briefly. For instance, in geomaterials, when we go and do the testing, and you just come up with a target modulus, the easy thing is that in the laboratory you can come up with a target modulus very easily with the seismic. And when you go and look at the field modulus, you see significant amount of variability and scatter. Is that device related or is it real? Well, the easiest thing is to dismiss as a device related, but it's basically, as I will show you in a second, it may be not the device as much as is a material property. I show you on a very, very controlled testing that we know we prepared 20 materials, quote unquote, identical. Pay attention, and use one layer of material. And we looked at the coefficient of measurement. If you look at different technologies, all of them, they had a coefficient of variation at around 29 plus minus 5%. And that's, you have to put it in the context. If you look at the change of MR, it's more than 3 times if you go within the standard 2 to 3% plus minus optimum moisture content. And what you see that, depending on the equipment you use, you're going to get a different modulus. This is a linear elastic. The interesting thing is that if you have 2 different lightweight deflectometers, you get different numbers. So that doesn't happen with different technologies and sizes. One thing is that we are lab curing and testing concrete, for instance. Well, we are not looking at the quality of construction and curing. This is what you would see. This is a lot of projects. I'm just putting it over here. You see that this, if the field, this is the field strength versus ideal strength, and you see that almost all the time, the laboratory modulus that we get is significantly higher than what we get in the field. The concrete, this is another example because we can make measurement in the lab and in the field, so we can go test, core, bring in the lab and test. So one of the things, for instance, we found for a project in Arizona, you can have look at the 10 different new construction sites, and you see that the target that you get from the laboratory testing is very difficult for a conscientious contractor to come up. So on average, they can give you 85% of what you get from the briquettes that you prepare. That's all I have. I just want to stop so that Nav can give you all the good information. And I guess at the, later on, I will be glad to answer questions that you might have. All yours, man.
Okay, let me see if I can.
Sorry, I've had difficulty with the Teams unmuting myself. Thanks so much, Dr. Nazarian. A very interesting presentation. Now we go to Dr. Nav from FAA, and we'll go over the questions after Nav's presentation.
Are you able to see my screen?
Yes.
Oh. So good afternoon, everyone. I'll be talking about modulus measurements in pavements using seismic methods. And let me start by saying that I am by no means an expert in non-destructive testing or technologies. I was introduced to PSPA by Professor Sohail Nazarian during a IPRF project, sometimes I think around 2004. So some of the information that I'll be presenting comes from that project. Okay, so I'll start with a brief introduction, where I work or facilities, full-scale test facilities, and then go into measuring concrete modulus and also measuring modulus of unbound materials, subgrade soils and aggregate materials, and then summarize my talk. So I work for FAA's Airport Technology R&D program that is located in Atlantic City, New Jersey. That's where FAA's William J. Hughes Technical Center is, and most of our research takes place there. Our sponsor is the FAA Office of Airport Safety and Standards, AAS 100 in Washington, D.C. And we provide research support for the development of FAA's advisory circulars. So when an airport uses Airport Improvement Program funding or AIP funding, which is a $3.5 billion a year program, they have to follow FAA standards and specifications. And we do research to provide information for developing those advisory circulars and updating those advisory circulars. Here is the people who are involved in our group. Our Airport Technology R&D branch has a safety section and a pavement section. And Jeffrey Gagnon is our manager for the payments team. And these are different programs under pavements that you see listed here. The full-scale test facilities and related to pavement design and non-destructive testing, etc. So as I mentioned before, FAA's Office of Airport Pavement, Office of Airports maintains these advisory circulars that provide guidance on airport development. They include pavement design, pavement materials, construction, etc. And all these documents are available from FAA's website. Next, I'll talk about our full-scale test facilities that are located at William J. Hughes Technical Center in Atlantic City. We have 2 full-scale test facilities, and then we also have a project or field instrumentation and testing where we go to different airports and install pavement sensors and also do material testing. Here's a satellite image of our facility. We have NAPTF, that is the full-scale test facility. Then we have material testing lab, a material processing facility, and then we have National Airport Pavement and Materials Research Center, where we use a heavy vehicle simulator. And on right of that, we have another facility that is under design. The construction should start sometimes in fall. It'll be a material testing laboratory because we have sort of outgrown our existing lab. And that's where most of our asphalt and binder related testing will take place. So National Airport Pavement Test Facility was set up in 1999. That's when it became operational. And here's a photograph of that. It's an indoor testing facility where we have National Airport Pavement Test Vehicle that runs on rails and has 2 carriages that can be configured for any current or future aircraft landing gear. Our test area is 900 feet long and 60 feet wide. The machine runs on rails. And we can apply up to 100,000 pound wheel load on a single wheel and up to 75,000 pounds on a 6-wheel landing gear. So if you look at the current commercial aircraft fleet, the maximum wheel loads we are looking at is around 73,000 pounds. So we have a lot more capacity available if the wheel loads go up in the future. This vehicle is fully automated. It can be programmed. We apply Wander in our traffic tests. And again, all those things are automatic. We can program and leave it. And let's say section number 2 fails, we can program the machine to load section number 1, lift the wheels over number 2, and then load back again. We can apply different wheel loads in different test sections. And the machine weighs roughly about 1.3 million pounds. Now, this is an indoor facility, so here we are looking at failures occurring in the lower layers of pavement structure. Because we don't have ability to heat the pavement, we really can't do much testing on asphalt materials. So to take care of that, we developed another research facility, National Airport Pavement and Materials Research Center, that became operational in 2015. And here we have 4 test lanes that are outdoors and 2 test lanes inside that hangar-like structure. And it's mainly meant for asphalt-related research. We use a heavyweight simulator that you can see in this photograph that has a temperature chamber. So we can heat pavement up to 120 degrees actually 152 Fahrenheit, 2 inches below pavement surface. And since we are testing surface layers, we are not worried about wheel load interaction effects. So we have a single wheel, which is a 52-inch tire that you'll find on A380 and Boeing 777. Again, we also apply wander inner tests. And even during winter months, when outside temperature is -10, -15, we can maintain 120 degrees or 130 degrees inside the test chamber. And then we have field instrumentation and testing project, because even though we can control temperature, or both full-scale test facilities, the testing is done under controlled conditions. And as we know, environment can have a very significant impact on pavement performance. So we go to different airports and install sensors in these pavements during construction time and then monitor performance of these pavements. And the photograph that you see here is from John F. Kennedy International Airport. The aircraft is actually standing on our instrumented slabs. We installed sensors in 4 slabs there. So next I'll go into the results from our non-destructive testing using PSPA. And most of this work was done on Portland cement concrete. So FAA's Advisory Circular 150/5370-10 provides specification for construction of airports. So this is where you'll find material specifications and construction specifications. It was released in 1959. The current version is -10H and was released in December of 2018, and it is required for use on all projects funded under AIP program. And you also get the website here on this slide from where you can download FAA's advisory circulars. So item P501 provides specifications for Portland cement concrete surface courses. And a typical stabilized, unstabilized base under it is P209, which is crushed stone. Now, if the airport is going to have aircraft that weigh more than 100,000 pounds, you're required to have a stabilized subbase. And there are 3 stabilized subbase options that are provided in the advisory circular. One is a cement treated base, P304, then there's a concrete base, P306, and P403, which is an asphalt stabilized base. The mixed design is based on 28-day flexural strength, ASTM C78. The minimum flexural strength required for concrete airport pavement is 600 psi. Now, in case of general aviation airports, or when the maximum gross weight of the aircraft is 30,000 pounds, 28-day compressive strength can be specified instead of flexural strength. Now, as we all know, with flexural strength tests, there are some issues, the repeatability and precision for these tests. And then the strength tests on lab cured specimens are different from the field cured. So the results are dependent on the curing conditions, and your slabs might have different strength or modulus because they're cured in a different way. So during construction cycle 2, is when we did these measurements, and the objectives of CC2 was to estimate early age strength development in concrete slabs, estimate modulus of concrete beams, cylinders, and slabs using seismic properties. And this concrete had 50% Class C fly ash. And the other objective was to demonstrate the application potential of PSPA and free resonant column tests for concrete characterization, and try to develop relationship between seismic modulus and different strength parameters. So what's a construction cycle? So when we start a construction cycle at NAPTF, we start with a set of objectives of what we want to learn during that construction cycle. And based on that, we do our pavement design, construct those pavements, and once pavements are constructed, we do non-destructive testing like falling weight deflectometers, PSPA, and other tests to characterize what we built, to look at variability within the pavement structure just after construction. And all these pavement layers are characterized during the construction. And once the construction is completed, then we start our full-scale tests, and we continue to do non-destructive tests during traffic tests so that we know how the pavement structure is changing. And once the test sections are failed, then we do post-traffic testing where we cut in transverse trenches in the pavement structure, remove one layer at a time, testing those layers, and then look at the failure mechanism. So construction cycle 2 had 3 concrete pavements. One was a 12-inch thick concrete pavement over 10-inch thick P154 subbase. So P154 is a uncrushed material. The CBR was had a subgrade had a CBR of around 7 to 8. Then we had concrete slabs on grade, and then we had concrete slabs on cement stabilized base or Econocrete P306 over 6 inches of P154 subbase. So the concrete thickness was same on all these 3 sections, just the support conditions were different. The concrete slabs were placed in a checkerboard fashion, so joints were created. And you can see some photographs from our construction cycle, the construction stages. So it was easy for us to collect samples, etc. And this is the photograph of after second placement. So during construction, we took 246 beams for flexural strength. 126 beams were for lab curing conditions, and 120 were put in the field right next to the slabs. And then we took 246 cylinders for compressive strength tests. 126 cylinders were lab cured, 90 cylinders were field cured, and 34 lab cured cylinders were taken for concrete maturity tests. Now, free resonance tests were performed on all the beams and cylinders in the lab before strength testing. And we used to take our field cured beams and cylinders to the lab that day. And those were also the days when we would do PSPA tests on our concrete slabs. And the curing conditions we maintained on our concrete slabs was the same that we did for our beams and cylinders. So any day we poured water over our slabs, we did that on the field cured samples also. And we also marked these slabs and cylinders so we knew exactly from which slabs these cylinders and beams came. So this chart shows flexural strength and compressive strength results and the relationship between them. So, that's something that you see in literature also within that range, 12 times square root of compressive strength. And this photograph shows the setup for free resonance tests, and there is an ASTM standard for it. And we did all these tests on each of the beams and cylinders just before they were broken. And the results from free resonance tests are shown on this figure. Red line is for the lab cured beams, and the blue line is for the lab cured cylinders. And what you see is that field cured samples showed initially higher modulus value compared to the lab cured, but then around 18-20 days, the lab cured samples started showing higher strength than the field cured samples. And on this figure, you see the modulus from free resonance tests for both field cured cylinders and the lab cured cylinders. Very strong correlation to compressive strength. The red line is for field cured samples or cylinders, and the blue line is for the lab cured cylinders. And this figure shows the modulus values from free resonance test as a function of flexural strength. And here for the field cured beams, the correlation was not that strong, actually very low, around 0.27. And for lab cured specimens, it was fairly strong. A lot more variability in the field cured beams. Then we also used PSPA, or Portable Seismic Properties Analyzer. And the idea was to characterize these concrete slabs, look at the modulus that these slabs have in the field at different ages. So PSPA is suitable for determining in situ seismic modulus of concrete slabs. And Professor Nazarian already talked about the principle on which PSPA is based. This is what the equipment looks like. And the PSPA can be used for determining modulus of asphalt and for concrete. So when this setup is for asphalt, and for concrete, what you do is remove the bars that connect the last set of receivers to the equipment. So basically the spacing between the two sensors, or the spacing between the source and the first receiver, and the first receiver and the second receiver are the same. It's a very convenient test because all you have to do is carry the laptop and the PSPA equipment. And at that time, the equipment used to have a rechargeable battery, but later on, the version that we purchased takes power from your laptop through a USB port. And that's how the signals from PSPA look that you see in this figure. And this figure shows the modulus values computed from PSPA as a function of age of those concrete slabs. Now, when you put these seismic modulus values on the plot that has modulus values from cylinders and plotted as a function of compressive strength, that's what you see. So the modulus values that we are getting from PSPA are very similar to what we got from free resonance tests in the lab on concrete cylinders. And similar thing for the concrete beams. So here the modulus is shown as a function of flexural strength. And again, flexural strength shows higher variability with modulus compared to the compressive strength. But the modulus values that we get from PSPA are in line with the modulus values measured from free resonance tests on the beams in the lab. Next, I'll talk about the modulus measurements on unbound materials, subgrade soils, and aggregate materials. So there is a different version of PSPA that is called D-PSPA, or the dirt PSPA. And it's very similar to the other PSPA, except that the source and the receivers are slightly different. So these measurements were made during construction cycle 7 at NAPTF, and the primary objectives of construction cycle 7 was to look at perpetual pavement structures. And then we also had some sections where we did some overload tests to determine allowable aircraft overload operations on flexible pavements. And these tests were done for International Civil Aviation Organization. And the secondary objective of CC7 was to look at the structural performance of drainable bases and investigate changes in subgrade CBR with moisture movement in the low strength subgrade. So subgrade here was CBR of around 3 to 4. And this is the layout of the test sections. The pavement thicknesses ranged from 5-inch for a conventional flexible pavement, and then we had 8-inch, 10-inch, 12, and 15-inch sections over P154 subbase and CBR 3 to 4 subgrade. This slide shows some of the material properties. The subgrade was a DuPont clay that had a liquid limit of 66% and a plasticity index of 33%, so high plasticity clay. Maximum dry density was 1 or 2 pounds per cubic feet. Subbase was a dense graded sand with silt. It meets FASP 154 specification, and the gradation is shown on the top figure. And the base was P209, which is a crushed stone. And again, you can see the gradation on the right-hand side figure. And we use D-PSPA. Again, it looks very similar to the regular PSPA. And this is the layout of the 5 test sections, and the dots that you see are the locations where we did PSPA tests, or D-PSPA, I should say. 6 tests were conducted at each location, 3 in transverse direction and 3 in longitudinal direction. We wanted to look at the effect of the direction of compaction on the materials. So these are the results from subgrade soils, subgrade seismic modulus, and you can see the coefficient of variation within these measurements were around 20%, which is fairly common for unbound materials. That's the kind of variation you see in the material properties. And the mean modulus was around 20,000 KSI. And in this figure, what you can see is there is not a very significant difference in the modulus that we calculated in the direction of compaction, which is the longitudinal direction, and the transverse direction. And on this figure, you see modulus values for P154 subbase, which is uncrushed material. Coefficient of variation was slightly higher, but again, within the range that you would expect in the field. And in this case, we saw higher modulus value in the longitudinal direction, which is the direction of compaction. So the roller was moving in that direction compared to the transverse direction. And we feel that this variation is because the materials are uncrushed materials. So they are realigning themselves under the roller in longitudinal direction. And that's why you see higher moduli value in the longitudinal direction. This figure shows PSPA modulus for P209 crushed stone base. And in the case of crushed stone material, we saw higher moduli in the transverse direction. And again, what we think is because the material is crushed, so you get very strong interlocking in the aggregate material. So under the roller, it is not reorienting themselves that much as your uncrushed material did. And that's why you see higher moduli in the transverse direction compared to longitudinal. And I think with that, I come to the end of my presentation. So I'll provide a brief summary of what we did. So we looked at the effect of type of curing on specifications, and we did see that effect. Compressive strength of field cured specimens was roughly 94% of the lab cured specimens. Flexural strength results showed significantly higher variability than the compressive strength results, and that's something we have all seen who have worked with concrete beams. Specimen curing did not have any significant effect on the relationship between compressive strength and flexural strength. The non-destructive tests performed on beams and cylinders, which were the free resonance column tests, and the concrete slabs we did PSPA, demonstrated a high degree of repeatability. And the biggest advantage was that the tests were rapid and easy to perform. Moduli obtained with seismic tests correlated well with the traditional strength parameters such as compressive strength and flexural strength. Relationships were fairly strong in the case of compressive strength because again, we see less variability in the compressive strength compared to flexural strength. Moduli obtained from PSPA and free resonant column tests were comparable. The strong relationship between the seismic modulus and concrete strength demonstrated the application potential of PSPA and FFRC tests for concrete characterization of airport pavements. D-PSPA tests were performed to characterize material properties of subgrade, subbase, and base during construction of CC7. D-PSPA tests were again conducted in the direction of rolling and also perpendicular to the rolling direction. The modulus of subgrade was found to be insensitive to the direction of rolling. The statistical analysis indicates that CC7 subbase has higher seismic modulus in longitudinal direction than the transverse directions. Again, we believe that's because of the material is uncrushed and the particles easily reorient themselves under the roller. And higher seismic modulus is found in transverse direction during compaction of the crushed stone base material. And some of these results are also given in this report that was done by Innovative Pavement Research Foundation. That was the Airport Concrete Pavement Technology Program. And this report can be downloaded from FAA's website. And the Appendix E of that report provides a draft specification for estimating concrete strength with seismic and maturity methods. And Professor Sohail Nazarian was one of the PIs on that project. And with that, I end my presentation. Here's a photograph measuring modulus on a concrete pavement at John F. Kennedy International Airport. And you have my contact information on the slide. So if you need any additional information, You can contact me, send me an email. It also gives the website of our branch from where you can download all our research papers and research reports. And thank you.
Thank you, Dr. Nazaria. Thank you, Dr. Garg. There's an echo on my side. I don't know. Thanks for the great presentation. Very informative, very comprehensive. I appreciate it. So there are a couple of questions. One is for, I guess, Dr. Nazarian about whether PSPA is still available commercially.
It's not. I think the production was discontinued around a year ago or two.
All right, thank you. And for Dr. Garg, based on your investigation, would you say there is an effective depth for DP spa? Either of you can respond to this question. Effective depth for DP spa.
Yes, I think there is an effective depth, and I think Professor Nazarian can give a better answer, more detailed answer for this question.
I think that, as Nav showed, you can change the spacing between the sensors. And the spacing within the sensors dictates what's the depth of influence. So if you want to go deeper, you just put longer rods. If you want to go shallower, you use shorter rods. And usually the depth that you see is roughly equal to the spacing between the receivers to 2 times that spacing.
Thank you. And another question is, what was curing condition in the field curing and lab curing?
Okay, so for the lab samples, we followed ESTM standard. You put all these beams and cylinders in a curing room where a certain humidity is maintained and a temperature and the moisture. Whereas for the field conditions, since the slabs were covered by burlap, we covered all our beams and cylinders also with burlap. And there was a set routine when they would water the slabs. And that's the same time we would also apply water to our beams and cylinders that were under the burlap. So the slabs and the field cured samples received the same curing. So our field curing was basically different from lab curing. I hope that answers that question.
Thank you. If you need ask a follow-up question, you can still write down your question, because we have about 15 minutes for question and answer, so it's pretty much a good amount of time to go over the question.
There was another thing I would like to add. Like, we also used PSPA on asphalt pavements, and there also results were very repeatable. One thing that we couldn't do and we tried was, we thought, once the asphalt paving is done, we know temperature is falling. So let's see if we can measure the modulus at that time, and if we can develop a master curve kind of thing. And that was something we could not do because the material properties are changing so fast as it's cooling. We had hard time getting reasonable, repeatable values. But once the pavement cools down, then the results were very repeatable and reasonable.
Thank you. Next question is, have you correlated modulus from PSPA and FWD?
We have not. We have not. The PSPA modulus, we do measure PSPA modulus as we are doing HWD, but we have never tried that. And maybe that's something I should bring to our NDT person. They should look at.
Can I jump in? There was an extensive TechStart project relating FWD and PSPA. I would be glad to provide the source. in the compute, if you run the chord modulus on the concrete and you compare it to the seismic modulus you get from free is the relationship is 0.75. The chord modulus is 75% of the seismic modulus, more or less.
Thank you. Next question, does this method compare to ultrasonic P-wave methods on concrete? Sohail?
Yeah, theoretically it should. We feel that surface wave is more robust than the compression wave for this purpose. But under the same circumstances, they should give you numbers that they're related through Poisson's ratio directly.
Can you talk? Oh no, there is one before that. Does the software allow to use a separate source to execute in PSPA? How to use a separate source?
No, you would not be able to put in. It's a self-contained device that the source is controlled by the computer because the strength of it. So it's very difficult to put an outside source on. Mm-hmm. But you can get all the raw data out and do the analysis the way you wish.
Mm-hmm. And you have also access to the source.
Yes. You have the source signature as well. Yeah.
Right. Can you talk a little bit about the underlying algorithm used in PSPA to back calculate the individual layer modulus?
I think it's for me, right? We do not do any back calculation. We do a direct measurement, and PSPA is only appropriate for the surface layer. We have done some work where you put two layers. We measure the first layer, and at the same point, we measure the top layer and do some inversion that way. But the algorithm is a forward calculation. There is no back calculation involved. So we assume that the layer is uniform, and you define what the range of thicknesses that you want the modulus, and it would just get a direct modulus.
And I guess the next question is also similar to this one, comparing SASW and PSPA.
Oh, okay. PSPA uses SASW with two receivers and one source. It just basically PSPA is the name of the device. SASW is the technique. So that's the difference. If you are doing SASW with different spacings and different range of frequencies, then you can do inversion. PSPA is not equipped to do that. It would give you the raw data and you can do your own inversion, but the device does not do that. One is a technique, the other one is a device to run that technique. It's just to simplify.
And I guess the SASW, you have more control on the source, on the receivers, the spacing, the number of receivers, but the PSPA is the device, like Nazarian said, that the source and the receivers are set, so you cannot change them. But with the SASW, you have more control on the test experiments.
Yes.
Another question for Dr. Garg. Would you comment on the most pressing issues FAA is currently facing for pavement reservation?
So, FAA pavements or airport pavements are designed for 20-year design life. And we did a study in 2004 that showed that if FAA standards are followed for pavement thickness design, materials, and construction, these pavements do provide you 20 years of design life without any significant maintenance requirements or repairs, as long as you keep following your regular maintenance needs. Now, recently, a couple of years ago, Congress asked FAA if we can design pavements for 40-year design life. So that's when it's going to become more critical, because now you have to make sure that your materials can last 40 years. And For 20-year design life, we were mainly looking at structural life. Now, functional life will also become very critical. So we are trying to come up with an indices that combines both structural and the functional part to estimate, like 40-year design life when you would consider your pavement failed. So for that, we are collecting material samples from different airports and looking at their PCI data collected over the years and analyzing that so that we can come up with the requirements for 40-year design life. Surface treatments are not very common on major commercial airports because of FOD issues and stuff.
Thank you. There is another question. Is there any feasibility to use the MASW concept to PSPA?
No, because MASW is a multi-channel, so you need for the proper, you need at least 12 to 24 channels, and PSPA has only 2 channels. So that essentially you cannot use it. With 2, you cannot do MASW with 2 sensors. You need at least 24, and you have to be careful. So it doesn't do that.
Thank you, Dr. Nazarian. I guess it relates to the last question. It goes back to your response, Nav. Are these needs going to be reflected on a BAA?
Is BA the broad agency announcement?
Right, I believe so. That's what it meant. Yep.
Yeah, there is a project on surface treatments that was recently started, but I think that project has been already awarded. Yeah.
All right. We don't have any more questions. I do have a question for Nav. And there is another question. If I ask mine, what are the challenges in your agency with regards to NDE implementation? Because in our industry, in highway industry, we are pretty familiar with the challenges that our industry is facing for NDE implementation. But what is like the top 2, 3 main challenges for NDE implementation in airports, pavement industry?
Well, in airports, the most important thing is getting time to do these NDTs because airports are not willing to shut down. So they only do it when they have some issue, or they just do it during their regular payment evaluation times, along with PCI survey. Now, FAA does not own any airports. So what they do is they have an advisory circular that is provided as a guide to the airports if you want to develop a NDT program. And some of the major airports, they actually have a very comprehensive NDT plan. They'll do regular FWDs, HWDs, and surface profile measurements, grooves. Those are the more critical things they look at.
Okay, great.
And I think very soon we'll be updating our advisory circular actually for NDT. Yeah.
Okay, and when is that going to be? When is that going to happen?
They will start working on it sometimes this year.
Okay.
So it should take about a year, based on whatever information we have collected. And Dr. Gabriel Bazi, he's the program manager for our non-destructive testing. So he'll be the one to contact if you need more information.
Perfect. Thanks for the information. Thank you. We don't have any other questions. I know that the question is directed to me. Yes, the recording is available, Amir. Please contact me directly if you need a link to the recording. Not a link, the file of the recording, because it takes a while to be uploaded on the YouTube channel. So if you need the recording, please contact me directly and I'll be happy to share the recording with you. So with that, I'm going to adjourn this webinar. Again, thanks so much, Dr. Nazarian and Dr. Garg. Great presentation. I really enjoyed the informative information and presentation from both of you. I appreciate you taking time from your busy schedule and contributing to this webinar series. I greatly appreciate it. And the next monthly webinar will happen on August 28th, and Caltrans will be sharing their experience with NDE on bridges. So I encourage everyone to attend the webinar. If you don't have the meeting information, let me know and I'll forward you the team's invite. So with that, thanks so much. Great having you, Dr. Nav, Dr. Sohail. Thanks so much. Have a great afternoon.
Thank you. You
so
too.
much.
Thank you, Ara.
Thank you.
Thank you, Professor.
Bye.
Bye.